So, here I will start with the comparison of radar and LiDAR. Okay. So, have a look here in this. I have just in a compact form I have given all the comparisons, and you will learn it as we go along. So, radar stands for radio detection and ranging, LiDAR stands for light detection and ranging. Okay. And types of wave. So, radar uses radio waves or microwaves. Okay. So, they are very long wavelengths, okay. While lasers uses light pulses, they are generally referring to visible and near infrared, those kind of those kind of wavelengths. Okay. So, these are very long wavelengths, and these are relatively shorter wavelengths compared to the radio waves. Okay. And here I say the light, what I have said in the previous lecture is that generally we would like to use pulsed light, but here I also write down continuous wave for LiDARs, because sometimes you may not be interested just in the time of light. You may be interested in say the spectrum, and then whatever is the reflected light that is coming back and forming a spectrum, that is good enough for you, and the time measurement is not important for you, then you can go in for a continuous wave. So, in that sense, pulsed and continuous wave laser light is used. Okay. Now, measures the time of flight of radio waves, that is an obvious thing, measures the time of flight of light waves. Okay. This is very obvious. Then radars have lower resolution due to longer wavelengths. Again, this is understandable, while light resolution due to shorter light waves. Okay. So, light waves are shorter in wavelength, so you can focus them also to a tiny spot, and the resolution will be more obviously between two particles, say, which is at a distance. You will be able to resolve them better than in a radar. So, these are the two distinctions between the two. Then typically within centimeters to meters, the accuracy. Okay. So, accuracy and resolution, they are of course related to each other. So, typical within centimeters to meters, that is because of the long wavelength. And then for LiDARs, highly accurate resolution within millimeters. Okay. That is because the light is shorter. Okay. Then what is the effective range of a radar? Effective range is long range, capable of detecting objects over hundreds of kilometers, while LiDARs are shorter range, typically effective within tens of meters. Okay. They are short range, and the radars are longer range. Range limitation of the radar is less affected by atmospheric conditions like fog, hail or rain, while in case of LiDARs, performance can degrade in fog, hail, rain or dust conditions. Okay, this is also you can understand from the previous lecture, that there will be too much of scattering. The fog, rain, hail, the particles are big enough to cause a lot of scattering. It will cause scattering, and your LiDAR light cannot pass through them. Okay, your object may be beyond the snow and the fog. Okay, the object that you want to measure, and that is stopped by the screen. While in case of radars, they can pass through these particle sizes. Okay, so it has a longer range in that sense. Performs well in rain, fog or low, that is the same. Bad weather performance is the same as the previous one. Struggles in adverse weather condition due to light scattering. Okay, so these two are sort of related to each other. And then surface penetration, can penetrate surfaces like clouds or vegetation. Oh, okay, yeah, cannot penetrate opaque or dense materials. As I had said in my last lecture, I mean, if you have to use that particular wavelength of LiDAR in order to penetrate through through say trees, trees and leaves and vegetation, in order to reach the ground part, if you want to map the ground part. Okay. So, that is surface penetration is better in case of radars. Then here I just give the applications. It can be used to detect vehicle movement, aviation and aerospace. There is a lot of application of radar. So, you know the position of these aviation military installations and such things, or aeroplanes, or whatever, satellites and such things. Okay. So, it is also used in meteorology, and it is also used in the military, of course, to detect military type of objects that is of interest to you. Okay. Here in case of LiDARs, the applications are mainly in mapping and surveying, that means mapping terrains. It is definitely used for military purposes also, and aviation and aerospace also it is used. If the range is smaller, you can detect aeroplanes or jets or something, or maybe the smoke coming out of jets and such things. So, that is one way of detecting. And vehicles, though not so much for detecting vehicles. Here I put vehicles last because there is a related technology connected with LiDARs. It is similar, actually it is similar, it is called tracking. From the name itself, you know, you have certain vehicles, either it is a celestial tracking. Do you want to track the position of the moon at different times of the night sky? Do you want to track artificial satellites which are there? You want to track their movements, or you want to track their change from the mean position and such things, or you want to track say a aeroplane or a jet or some flying object. Okay. So, in that also it is called tracking, but it has a similar thing like a LiDAR. Only thing in tracking, what happens is, quite often at that reflector part, here is your source of light, it goes to the reflector and comes back. So, what is done is the return light takes the same path as your the emission light. That is the whole point of the problem. Okay. So, you have to have some element which will give this sort of a time of flight. While in case of just in general LiDAR, I have shown you this can be your emission, and you can have any path, and this can be your detector. There can be an angle between them, it need not be exactly. Now, the point of this exact thing is that is what tracking is about. Generally, this is done by keeping a retro-reflector. Retro-reflector is on your object. Suppose you have a prism is an example, or you can have mirror which are at 90 degrees with each other. Okay. So, in a prism, the light will go from here and it will come exactly. So, these two lines will be parallel. Same thing here. Suppose you have these two mirrors at 90 degrees. So, you go here and come back here. So, these two, the going and the coming light, are parallel to each other, and that is how you do the tracking. So, you have to keep a tracking device, which may be a retro-reflector, on the object that you are tracking. And then as the object moves, your light that is going there and coming back will always be parallel to each other, but you can move your total experimental system at the ground level. Okay, at the ground level, and you are sort of, this system is moving along with the signals that are coming back from your object. So, it's the principles are same, just some instrumentation have to be fine tuned to get it to track. Okay. So now we come to the cost. Cost, of course, it says radars are less expensive for the basic systems, okay, not the paraphernalia which you have, the deconvolution system to getting a 3D map, or the software and all that is required, or the different kind of detectors. It's only the basic radar system. Okay, that is supposed to be less expensive than when you have precision optics and lasers. These are more expensive. But then quite often in many cases, in case of LiDARs, the total system becomes more expensive because you need instruments to connect to, say, your GPS. You need instruments to give you a 3D kind of a map, and you need instruments which will convert, say, a terrain from just a set of signals to the actual look of the terrain, or you have to analyze your spectrum that is coming into your detector, all such things. So you need a spectrometer. Then this becomes really very, very expensive. But then again, it will add to the cost of even your radar for such things. So there is a sort of which one is costlier. It's difficult to judge, but on an average, maybe this is the thing. And each of them has their own kind of pros and cons. So depending on the system you're trying to do, you will use it in that. Okay. So here I stop my discussion on LiDARs. But there are so many variations of LiDAR, especially the ones that are used for atmospheric sensing, that that it's and there are many types of LiDARs. So for that you have to really go deep down into the research that has gone on in this direction, and a lot of research has gone on in this direction. Okay. So I leave it to you to read those if you are interested. Okay. Now we will go on to another property of laser, which another property of lasers which we haven't used before. So this property, see, till now we have in medicine the power and the intensity of the laser is important. The wavelength, choosing the wavelength is important. Then in LiDARs we saw that the low divergence of a laser is a characteristic of laser light itself, which is being used. Now here I use the characteristic of pressure that light applies. This may come as a surprising property of a laser, but I have mentioned it before, if you remember, in my previous lecture. But surprising in the sense, nobody thinks of light putting pressure on anything. Nobody thinks of light forcing something to move from here to there. But then it does have pressure, and it is proportional to the intensity of the light. Okay. So with lasers, one can make a force large enough to accelerate, decelerate, deflect, guide, and even stably trap small particles. And I put a little bit of emphasis on this because not in the very far past, Nobel Prize in this direction has been won. In 2018, the Nobel Prize was given to Arthur Ashkin for the tweezers, for able to use this fact of light, that is light inserts pressure on an object, actual physical pressure, and you make that light do a lot of work for you. So we know what kind of work is going to be done by this light as we go through this lecture. Now the thing is, it's not that Arthur Ashkin thought of it first, that light exerts pressure. It was thought of by Kepler, famous astronomer. You must have read about Kepler. of when we study celestial bodies, and Kepler's name always comes into the picture. So what he found is, if you just focus your attention to this picture here, what he found is that these are comets. This is the sun and these are comets. And comets all have a long tail. They all come with a tail. Okay. And that too, two tails. This bluish kind of light and this white kind of light, both are tails. There is a bluish kind of light and a white light, it is a tail. But then this head of the comet always faces the direction of the sun. Wherever they may be going, maybe rotating around the sun or some other planet or whatever, the head of the comet always there, and the tail points away from the sun. Okay. This is an animation picture, but then that is what astronomers have observed over time. And this is way back in a different century altogether. Okay. So the very fact that this happens, they realized that the sun's radiation is actually putting pressure on those particles of actual particles, rocks or small particles of this comet, and they are pushing it out. So that is why this tail is always facing away from the sun, because the sun's radiation itself is pushing all those small particles in a comet. The comet comes with a head and lots of small rocks or pieces, and all these are there. Okay. And there is of course a blue tail also. This blue tail of course is because of ionized particles that are there. So I won't speak about that. So it comes with a blue tail and this white tail that you can see. So we are more interested in the white tail, which are actually neutral particles. They are all neutral particles, but still they are being pushed out by the sun's radiation. The blue, of course, they are charged particles, so there are many forces acting on those charged particles, and that is how it is moving away from the sun. Okay. So our interest, or the interest of Kepler, was on this, and he is the one who could prove convincingly that it is because of the sun's radiation. Okay. So that is where the pressure of light, pressure of radiation comes into the picture. Okay. And once you know that, you are able to manipulate neutral particles using lasers. So this is what Arthur Ashkin used. The idea was from here, but he cleverly used it to manipulate neutral particles, and especially in biological systems. That is why it has become so important and famous. Now how does it work? Say a focused light beam of 1 watt power approximately, okay, and you have a particle of radius which is tiny. So we will not talk about the celestial bodies anymore, but we will talk in the lab, things that can be done in the lab. Particle of radius 1 wavelength. So the force that is applied on such a particle with a laser of say 1 watt power is approximately 10 to the power minus 3 dynes. Okay. See, one more thing that I want to remind you of is, remember when we were speaking about the nuclear fusion. In that we had on the fusion pellet, we had lasers from all directions hitting that pellet and creating a large pressure which made that pellet to collapse. So here again the laser light was putting pressure on that pellet. That was the light pressure. So light pressure P is proportional to the intensity, and we had gone up to very high intensities here, remember. They were in petawatt level in power, so the intensity is watts per centimeter square. So depending on how tightly you focused it, your intensity will go up. So there also that power of the laser was exerting pressure. But there the pressure was in the scale of 1000 megabars. Okay. So, it was in the scale of 1000 megabars. Here what I am speaking about is in terms of 10 to the power minus 3 dynes, small things. It is small, it is not as huge pressure as that. Okay, you can just have a, I think I am speaking of megabars here. So, dynes in megabars is 1 bar is equal to 10 to the power 6 dynes per centimeter square in CGS units, CGI units. Okay. So, just to give you a comparison, these are just units, you can change it from one to the other, you can put it in pascals if you like, give that conversion. So, in any case, the idea is that the light is giving pressure. And so, what Arthur Ashkin did in a lab, he used transparent latex spheres, he used spheres, like this, spherical objects, and he used a argon ion laser, and he used a wavelength of 0.5145 micrometer. Okay, this is a small m, micrometer. So, argon gives out in the green region of light, and a spot size he had, which he used in this experiment, was 6.2 micrometer. This m should be a small m, not a capital M, small m to tell you micrometers. And he used a TEM00 mode. Okay. And he only required a milliwatt power, not much, milliwatt level of power. So, this milliwatt level of power could exert the pressure and move these particles, these small spheres that he used. Okay. How, I mean, it seems unbelievable, but then it has happened, okay, and he has seen it experimentally. Okay. So, how does it happen? So, this I call it Arthur Ashkin's light trap. So, here is the green laser beam. This is a green laser beam, because it is a green light, I just put it there. And that central part is slightly darkish, because it is a TEM00 mode. It should be a TEM00 mode, and that is the most important part of trapping all these particles, and these are your latex spheres, the ones shown in yellow. Okay. And here I just put this as a Gaussian curve here, because the TEM00 mode, the spatial profile is a Gaussian curve. That means the intensity is maximum in the center, and in the wings the intensity goes down. Okay. It is important for it to be a Gaussian profile. It is important for it to be a TEM00 mode of the laser. Okay. So, you will understand that. So, here it is, these beads start moving along the laser light. That means as though the laser is guiding those small particles. Okay. Here I just give the spot size of the beam, and this is the total beam, and the spot size is given by W0. Okay. So, now see the spot size is slightly bigger than your spherical particles. Okay. So, this is what it does. Okay. Then with the same picture, what you can do is you can have a gradient force here. I will be explaining what is meant by a gradient force. So, you've moved the particles from here to here, and it's moved here, and because of the gradient force it may not move any further. It may just get trapped here. Okay. Another thing that can happen is you can levitate the particle. Suppose you are doing it from the other side. So, gravity is happening in this direction, and the laser is actually guiding the particle to go up. So, under some proper conditions you are able to you are able to you are able to overcome the gravity. That particle is able to overcome the gravity and move up, all right. And then in the final thing what he did was, he was able to focus one beam this side and one beam from that side and focus it and hold the particle here. This is what is called tweezing. So, he had made a tweezer with this laser light. So, he was able to pick up one particle and hold it with the laser light. Okay, so this was a fantastic discovery and fantastic experiment. So, small transparent spheres are set in motion when they are illuminated with laser light. Arthur Ashkin demonstrated that it really is radiation pressure pushing them, not anything else. See, they are neutral particles, there is no electrostatic force or electrical field or anything. It is the actual pressure pushing them. He was able to prove that. And one unexpected effect was the gradient force that pushes the spheres towards the center of the beam, where the light is most intense. So, somehow there is you wouldn't have thought of it. All these particles, suppose you have some particles here, they all move towards the center and they move along like obedient children going in a line. Okay. This is because the intensity of the beam decreases outwards and the sum of all the forces pushing the sphere sends them towards its center. And here of course, the sphere levitates by pointing the laser beam upwards, and the radiation pressure counteracts gravity. The laser beam is focused with a lens, the light captures the particles and even live bacteria and cells in these optical tweezers. So, the success of all his experiment was he could hold a live bacteria, imagine such a tiny object, in a position like this with a laser. In my next lecture, we will go on to see how exactly this happens. What are the underlying physics involved in such a case.